we're talking chapter 4, and we're talking about isotopes. So once again, a reminder, as we finished up on a little bit earlier, isotopes are the same element, but they have different masses. And as we talked about earlier, the protons are the most important thing in terms of what element you're dealing with. So in order for them to be the same element, they have to have the same number of protons, but different numbers of neutrons. And that is the main sort of difference in terms of isotopes. Same protons makes them the same element. Different numbers of neutrons is what gives them a different mass. And as we talked about there and kind of finished up on, if I can find it, where did it go here? I'm going to do it right now, yeah. So I think this is where we were at. There we go. So as we talked about earlier, when we write an isotope, we can use the symbol, which is represented by X. And on the top left there, we could do the mass number, which, as we talked about, is the number of protons plus the number of neutrons. On the bottom left there is our atomic number, which is our number of protons. Remember, as we talked about, only the atomic number, the number of protons, can be found on the periodic table. That, again, is the number that's on top of the symbol. Once again, the number that's below the symbol is not the mass number. That's the atomic number, which is something different. So as we talked about earlier, everybody needs to be whole numbers. They all need to be positive whole numbers. When you calculate protons, electrons, neutrons, atomic numbers, or mass numbers, that has to be. So as we were finishing up on, just to come back to this one, hydrogen, for example, has a couple of isotopes. Hydrogen, there's deuterium, which is sometimes referred to as heavy hydrogen, and there's tritium, as I mentioned at the end there, which is basically the radioactive version of hydrogen. Now, if we were to sort of write our symbols for all these isotopes of hydrogen, I would look here and see I have one proton. If I wasn't sure what the symbol of hydrogen was, once again, I would go to the periodic table and I would search out number 1 that's up on top, and obviously it will say H is the symbol for hydrogen. So for hydrogen, we would use H. The atomic number is the number of protons, which is 1, and that would go on the bottom left. Now remember, the mass number is the protons plus the neutrons. So our mass number, in this case, can be 1 plus 0. As we also talked about last time, hydrogen is the only element that does not have neutrons. Everybody else will have protons, electrons, and neutrons. So hydrogen has a lot of interesting sort of characteristics, which is why you do see hydrogen up there on the periodic table on the left. In an older periodic tables, you would also sometimes see hydrogen on the right-hand side as well, on both sides. And again, it has some interesting properties we'll talk about as we go through different chapters. So if we add that together, that obviously gives us a 1 for the mass number, which would be up on top. So this would be the symbol for hydrogen's isotope. Mass number up on top. And atomic number over here. That means if you do have the isotope written in this form and you want to figure out the number of neutrons, you basically take the top number minus the bottom number. So if you take the top number 1 minus the bottom number 1, gives you 0, which is the number of neutrons that hydrogen has. Any questions on that in there? Now we go to deuterium, and it doesn't even sound anything like hydrogen, right? But when I see that it has 1 proton and 1 neutron, as soon as I see that it has 1 proton, I know I could go to the periodic table because that's the atomic number. And even though, again, deuterium doesn't sound like hydrogen, I know ultimately because it has 1 proton, it is still hydrogen. And that is the symbol we would use, even though it has a different name in a sense. It would still be an atomic number of 1 on the bottom there. But now when we get to deuterium, it actually has a neutron, which means the mass number for deuterium is going to be 1 plus 1, which is 2. And that is what would go up on top for our mass number. that would be the mass number for deuterium, which is an isotope of hydrogen. And I know it's an isotope of hydrogen because it also has one proton. It basically is hydrogen with a different number of neutrons. Again, if you take the top number 2 minus 1, gives you 1 neutron. So this isotope of hydrogen has 1 neutron. Regular hydrogen has none, and that is the mass difference between those two. Again, they are still hydrogen, basically. Yeah. Now we come to tritium, which is the radioactive version of hydrogen. And again, maybe doesn't sound like hydrogen to you, but when it says 1 proton, I'm still going to go to the periodic table and find my hydrogen symbol. And it's still going to have an atomic number on the bottom of 1. In this case, though, it has 1 proton plus 2 neutrons, which would give me 3 for the mass number. And 3 would go up on top. So although they all have kind of different names or go by different names, they are all ultimately still the element hydrogen. Again, the difference between them is the number of neutrons that they possess. Any questions on the mass numbers on top, the atomic numbers on the bottom left? Yeah. The atomic numbers on top on the periodic table. But when you write the symbol, the atomic number goes bottom left on the symbol, and top left is the mass number. It is, yes. That is actually the atomic mass, as we talked about earlier. It is not the mass number. So we'll talk about that a little bit later on in our chapter as well. But that's the atomic mass of the element. Other questions? Okay. Now, these are, I would say, very common ways that you write sort of the isotope and its mass number and atomic number. Sometimes you do see it written another way. So, for example, if I have this, which is Cu-64, right? Now, when I see Cu, Cu is copper. And if I want to know what the 64 is, I can make a pretty good guess, perhaps, because if I go to copper on the periodic table, which is Cu, what number is above copper on the periodic table? Number 29. And this is the atomic number, right? Which means obviously the 64 here is not the atomic number because the atomic number for copper there is 29. The 64 in this case is the mass number. And that also is a very common way that isotopes are written, symbol dash a number, and that number again represents the mass number. So if I were to kind of turn this into the other version of how to write the symbol, it would look something like this, which is, get rid of that there. And we would have obviously copper. This would be our mass number, which would go up on top. Our atomic number we could get from the periodic table, which would go bottom left. And again, these are basically the referring to the same isotope in this case. Yeah. In terms of how to write it, is that what you're asking? Yeah. So I would say honestly, in most cases, in sort of classes like ours, this is probably how they want you to write it and how you probably should write it in this class. I would say sometimes in reading books or like experiments or if you're doing stuff like that, this is a very common way that isotopes are written. So technically they're both represent the same thing, but I would say probably for our class and even like 1B when you get there and stuff like that, they usually want to see both the mass number and the atomic number written. So, and even 1A as well. So I would probably write it more with the like this way here on the right. Yeah. Other questions? Yeah, so that, again, that is not the mass number on the periodic table. That's the atomic mass, which is something different. And that is also what confuses a lot of people because very commonly a lot of isotopes will have a mass number that's very similar to the number that you see on the periodic table. And that's honestly because it's all based on how many protons, electrons, and neutrons you have. So a lot of times what people think is kind of like what you said there. Oh, they must have maybe just rounded the number and that's how you get it. So that is definitely, again, not how you get the mass number. you will have enough information in these type of problems to calculate it yourself, and also you'll have enough information to figure out the neutrons based on the information given to you. Other questions? Now, what this means in this case for my copper, right, is how many protons would my copper have in this case? My copper would have protons 29, right? Atomic number. Because this is neutral, right? And I know it's neutral, by the way, because there is nothing written up here. There's no charge in the upper right-hand side of the symbol. That is typically where you see charges written, like a +2, a +1. So if you see nothing written there, it is assumed that it is neutral. And again, they will write the charge if there's something with a charge. So because it's neutral, that also tells me in this case, electrons I should have an equal number of electrons to balance it out. Because if you have 29 positive guys and 29 negative guys, that gives you no charge overall. And that is why it's neutral. If I want my number of neutrons, we take our mass number, which is the top number, minus our atomic number, which is the bottom. So my number of neutrons in this case would be mass number 64 minus atomic number 29. Gonna hit us with about 35 neutrons in this case, yeah? 35 neutrons. Any questions on that? So you can safely assume if you're doing these type of problems that they are neutral, unless it says something like it's an ion, which is something that has a charge, or it gives you a symbol that has a charge, then you have to kind of take into account those things. But if it doesn't mention any of that, or you don't see any charges, again, a lot of times you can assume that it's going to be neutral. And we'll talk about what to do when it does have a charge in just a second here. All right, so why don't you give these a try here and see what you come up with. I'll write them a little higher. I know it's kind of hard to see in this room, so 6027 on that. We got 3717 Cl and a 23892 uranium here. All right, we're looking for number of protons, number of neutrons, and number of electrons in each of these. So take a few moments and calculate it up. See what you come up with. All right, let's take a look. So first off, CO is cobalt. Once again, as we talked about, bottom number, atomic number, top number there, mass number. So again, our number of protons plus number of neutrons. All right, so obviously before I scribbled all over it, there's nothing written there, so we do know it's neutral. So we'll start with the number of protons here. It needs to be 27 in this case. Again, equal to the atomic number, which is 27. If you want to put a little plus next to it, so you know you got 27 positives. Because it's neutral, we know we need to have an exact same amount of negatively charged particles like electrons. That again, by the way, gives us an overall charge of 0 when we add all of our positives and negatives together. Once again, our number of neutrons is going to be our mass number, which was 60, minus our atomic number, which was 27. And I'm going to go with 33, I hope, there for our number of neutrons. Any questions on that one? Looking at the next one, once again, we do not see anything written here, so we could assume that it is neutral. We're going to go number of protons, which is our atomic number, which is 17, that we could get from the periodic table. Number of electrons, going to be neutral, so exact same number of electrons, which once again gives us no charge when we add those together. Our number of neutrons is going to be our mass number on top, minus our atomic number, so 37 minus 17, 20, I think, in that case there. Any questions on that one there? Cl obviously is chlorine. U is uranium, and same deal. We're going to go no charge on it because nothing's written there. Number of protons going to be our atomic number, which is 92. Number of electrons going to have to match because we have no charge. Again, giving us no charge overall. Lastly here, number of neutrons. Mass number 238 minus 92. That's a lot. 146 we'll go with off the top of my head there in terms of our number of neutrons. Any questions on any of those there? Yeah, it's got 20 there up on top. Yeah. Other questions?
Or does that come to play when we have a number with a charge?
I'm sorry, saying one more time. Is neutrons always zero? Is that what we're asking? That's not the number of neutrons. That's the overall charge is zero. Yeah. So remember in an atom, right, there's only three particles. There's protons, electrons, and neutrons. Neutrons have no charge, which means that it has no effect on the overall charge of the atom. So it's only protons and electrons that can affect perhaps the overall charge of it, and those are the only things that have charges. So if it's neutral, that means the protons and electrons has to be the same number.
Never, do they always equal the same as the proton itself?
They do not. If they do have a charge, they will not. But if it's neutral, they will. So if there is no charge on the atom, then they should be equal to each other. Otherwise, you have, if they're not equal to each other, as we'll talk about, you'll then have more protons, say, than electrons. So then you'll be more positive than negative. You'll have a positive charge. Or if you have more electrons than protons, then you'll have more negative charges than positive charges, and you'll end up being overall negative. So when something has a charge, either positive or negative, it's a result of not having the same amount of protons and electrons. Neutral is a result of same protons and electrons. Other questions? Okay. I want to try a couple more here. So for each of these, why don't you write the symbol with the mass number and atomic number for each of these situations. That is krypton with 48 neutrons. That's nitrogen with 6 neutrons. And iron has a mass number of 56. How many numbers of protons, electrons, and neutrons does it have? All right. Obviously, krypton here, in case you can't see the periodic table on the wall, 36. Nitrogen, 7. And that was iron, which, by the way, is Fe, 25, 26. All right. So we're looking for mass number, atomic number symbols with the symbols. And for the last one, how many protons, electrons, and neutrons it has. Okay, so let's take a look here. Once again, if you're not sure, you would want to use the periodic table, obviously, as your friend here. You want to go find krypton symbol, which is Kr, so we would write Kr for krypton. Obviously, also from the periodic table, you could get directly from it its atomic number, which is 36. Once again, that is going to go bottom left when we write it. We do need the mass number, which is, again, our number of protons plus our number of neutrons. So we do know of protons is our atomic number, which is 36. Here they did give us the number of neutrons. So all we have to do is just add that stuff together there for a little 84 action, which would go up here on top. Any questions on that one there? Same deal here. If you're not sure nitrogen, go to periodic table, find nitrogen symbol, which is N, and that is what you'll write. Once again, the other important piece of information is going to be the 7 that comes off the periodic table. That's going to be our atomic number, which is, again, also our number of protons. That's going to go bottom left. Now that we have our number of protons, we could calculate our mass number, taking our number of protons, which is 7, plus our number of neutrons, which was given to us, which is 6, 13, and we'll go a 13 up on top, and now we should be in business. Any questions on those two? Lastly here, we want iron, and they actually give us the mass number here. So if you weren't sure, iron is Fe. They gave us the mass number, which is 56. From the periodic table there, we could grab the atomic number, which looks like 26, and that would be our symbol in this case. And because the atomic number here is 26, that means the number of protons would also be 26. The number of electrons would have to match as there is no charge or anything. So it is neutral, so all the positives and negatives cancel out. And our number of neutrons in this case would be our mass number of 56 minus our atomic number of 26, which is 30. So if any questions on how to write the symbols, figure out protons, electrons, neutrons, figure out mass number, atomic number. Obviously, you need to be able to do that. So earlier there was sort of a question, and we started talked a little bit about if something has a charge, what happens. So let's talk a little bit about sort of what happens if things do have charges. And if things do have charges, they are what are referred to as being ions. And ions are things that have charges. So just maybe slap that right here, I think. So ions are things that have charges, either positive or negative. And there's really two types of ions we come across. There are what are referred to as cations, and cations are positively charged ions. And there's also anions, which are negatively charged. So to illustrate what happens when something gains a charge and sort of what happens to our protons, electrons, and neutrons, let's take a look at both of these guys here. Let's start with the nitrogen. Let's say we have the exact same situation here, nitrogen with 13 for the mass number, 7 for the atomic number, and it has a -3 charge in this case. So because it has a -3 charge, this is what is known as an anion. Now, we want to kind of think about what happens with each of those subatomic particles. So, first off, the number of neutrons in this case is going to be the same because the mass number is 13, the atomic number is 7. That is going to give us 6 neutrons, right? That leaves us really, when we think about it, only 2 options in terms of how we could get a charge. And that is either protons, which are positively charged, or electrons, which are negatively charged, as neutrons are neutral. So it really doesn't matter if you got a bunch of neutrons, lose a bunch of neutrons. It's not going to affect the charge because it has no charge associated with it. Now, one of these 2 options, either the protons or the electrons, is not the answer in terms of what changes. If you had to guess, which one does not change, protons or electrons? It is the protons, because as we talked about earlier, right, it is the number of protons that determines what element you're dealing with. So if I wanted to get myself here a -3 charge and I want to take away like 3 protons, would that still be nitrogen? It would not, right? It would be now 4 protons, which makes it beryllium perhaps, and definitely not nitrogen. So because the protons and the atomic number, which are the protons, determine the element, the protons are not what changes when somebody gains a charge, because if it did, you would change the element. So we know here as well, the atomic number is still 7, and that would be the number of protons we would have in this case is still 7 protons. I'll put 7 positives next to it to indicate, obviously, that they are positively charged. That would mean in this particular case, how many electrons would I have to end up with a -3 charge? Those are both answers. So let's see which one is right here. The number of electrons in this case would have to be 10 electrons. And that is because if you take 10 negative things and you add them to 7 positive things, you are left over with a -3 charge, which is exactly where that charge comes from. And it's because in your atom at this point, you now have 3 more electrons than you do protons, and that gives you a net -3 charge because you have 3 extra electrons, right? And that also answers what happens when we look at anions. When we look at the neutral nitrogen here, neutral nitrogen had for protons 7 protons and 7 electrons, right? And that gave us an overall charge of 0. As we go from no charge to charge, it gained electrons. And that's what the negative sign means when you look at a charge. Negative means that it gained electrons. So something that is negatively charged has gained electrons. And you know how many electrons it gained? Is whatever the number is. So 3 minus means from the neutral nitrogen, this thing gained 3 electrons. And that's what the number means, is how many electrons it gained. You essentially could just take the atomic number and add 3 to it. It'll tell you how many electrons you need in that case. So an anion is formed and somebody becomes negatively charged when they gain electrons. The end result of that is they will now be an atom that's now an ion that has more negatively charged electrons than positively charged protons. And that's what gives us that net negative charge. Any questions on that there? Now let's take a look at the iron. Let's say iron here, we have the exact same guy, 56, 26, and we're going to give it a +2 charge in this case. Because it has a +2 charge, a positive charge, this is a cation, something with a positive charge. The number of neutrons here is still going to be the same as what we had above. It's going to be the 56 minus the 26, which would give us 30. Once again, much like the nitrogen, because this is still iron, it has to have iron's atomic number and number of protons. So this guy is still going to have 26 protons. That means in this case, to end up with a +2 charge, how many electrons does it have to have? It has to have 24 electrons. If you take 26 positive things and add it to 24 negative things, that's going to leave you a +2 left over, which is where the charge comes from. Basically, in this case, we actually have more protons than we do electrons. So we have more positives than negatives. And that's what gives us our net positive charge in this case. This is known as a cation. If we compare from the neutral, which was 26 electrons, to our guy with a charge, which is our ion, has 24 electrons, it lost electrons. And that is what cations do. Cations will lose electrons. And as they lose electrons, they now have more protons and become more positive. So when you lose electrons, you become more positive. And obviously, when you gain electrons, you become more negative. Typically speaking, when you look at elements, as we will talk about, metals typically are the ones that will lose electrons really easily and become positively charged when they do gain a charge. And nonmetals typically will gain electrons and become negatively charged. It is important to point out that on the periodic table, if you took any element on the periodic table by itself, not combined with any other element, they are always neutral. Things only gain charges when two things come together. More specifically, when a metal and a non-metal come together, that's when they actually gain charges. But if you have a metal by itself, has no charge. If you have a non-metal by itself, has no charge. Again, they only gain charges when they kind of come together, metals and non-metals. Any questions on that there? So why don't you try? I want to say we had, actually, I'll just get rid of those guys here. Let's go with, let's go with this, and I don't know. How many protons, electrons, and neutrons does this have? And then let's do, well, I don't know. Let's go. Okay, so let's take a look. So once again, we have really everything we need to kind of answer this question. First off, we could just look here to our bottom left. We actually don't need a periodic table in this case because we have the number, and that is our atomic number, which we obviously know is our number of protons in this case, which would be 19. Our number of neutrons is always the mass number, which is the top number, minus the atomic number, which is the bottom number. And in that case, that would be 40 minus 19 and 21, maybe. Yeah, looks good. Now, in this case, as we know, it does have a charge, and here it has a positive one charge. And like most things in chemistry, we typically don't write the one. So again, you just kind of write positive or negative if it's one positive or one negative. We should know a couple of things. First off, this is a positive charge, which means this is a cation. And the only way you become a cation is you lose electrons. So in this particular case, since this has 19 protons, which are positive, it would have to have, in terms of electrons, one less electron, because now if we take our positive 19 protons plus our 18 negative electrons, that's going to net us a plus one proton charge. And that again is where that charge comes from. So we should have 18 electrons in this particular case. Any questions on that one? Neutral potassium would have 19 electrons, right? So again, if it was neutral, it would be equal. We take a look at the next one. Once again, we have the atomic number given to us, which is 16. So right off the bat there, that's our number of protons, which is 16. We could do our neutrons. Number of neutrons is going to be 34, which is our mass number on top, minus our atomic number, which is 16, and 18, I think, on that deal. Now, our number of electrons in this case, once again, we do see a negative charge. That tells us it has gained electrons. It's an anion. The 2 tells us how many it gained. So really, I just need to add me 2 to that there, and that would get me 18 electrons. 16 positives, 18 negatives, leaves you a minus 2 left over, which once again is where our charge comes from. So again, if something has a charge, the absolutely only thing that changes is the number of electrons. And again, if it's positive, it should have less electrons than the neutral. And if it's negative, it should have more electrons than the neutral. And the actual number of the charge will tell you basically how many electrons either lost or gained, depending on the situation. Any questions on protons, electrons, neutrons, or things with charges? So, yeah. So as we've been talking about, the chemical properties of elements are determined by the protons and the electrons in the atom. Under normal chemical reactions, neutrons are not involved at all, as we've been talking about. Really, it's just the electrons. So one of the sort of benefits of isotopes, or nice things of isotopes, is you could have an isotope of a particular element, and it would do the same sort of chemistry as, say, for example, if that isotope was radioactive, it would do the same chemistry as the non-radioactive version. So maybe you're studying some type of protein where there's, say, copper involved, and maybe you want to know where the copper goes throughout sort of the process. You could use a radioactive version of copper, like copper 64, and you can basically follow exactly where the copper ends up and goes by following the radioactivity. And because this copper 64 is the same as kind of neutral copper or non-radioactive copper, it will perform the same chemistry in the body or the system that you're doing as well. Some isotopes of elements are radioactive, which could also be used in medicine as well, right? So they could use them to treat certain cases of diseases. They could also use it for scans as well, because they could give you something that's radioactive and then it kind of highlights and they can see everything in terms of scanning you. Let's talk a little bit about the periodic table. So there's our periodic table hanging on the wall there. So let's talk about some of the important things about the periodic table. First off, obviously the periodic table is an arrangement of the elements. There were spots left open as they were kind of putting the periodic table together to sort of fill in other elements along the way. Gives a good deal of information in terms of the elements, as we've seen some of that already, like the atomic number, right? We can find up there, which will tell us our number of protons, our atomic mass, which, as we'll talk about in a later chapter, can tell us the mass of those elements. Let's start with a couple of important things, which is the first off, elements in a column on the periodic table are known as a group, or if you're really old like me, nobody says it these days. A family, sometimes they're usually called, but most people these days roll with groups. Groups are up and down on the periodic table, yeah? So you go up and down on the periodic table. That is your groups. When you look at a periodic table, such as the one we see here, those are numbered up on top. And you oftentimes will see a few different types of numbering when you look at it. My periodic table will stay maybe-ish. Not a stay. There you go. You may even see, if you can see it up there, the one on the wall, also some different numbering. On a lot of periodic tables, you'll see some numbering that sometimes have A's next to it, sometimes referred to as the A numbering or the representative numbering. You may also see some numbers that have B's next to them. And you will also sometimes, like up here as well, and up there as well, probably, you'll just see a regular old 1 through 18 numbering system as well. So there's multiple ways that groups are numbered. The way that we use in this class, and pretty much all your chemistry classes, is we use the A numbering or the representative numbering. And what that means is if you look at the periodic table, right here is group number 1. By the way, group number 1 does not include hydrogen. Even though hydrogen's hanging out there, group number 1 starts right here with lithium. Hydrogen is not part of group number 1. We'll talk why that is in a second. Right next door is group number 2. It is 2A, but most people don't use the A. They just call it group 1 or group 2. But usually when they say that, they're talking about group 1A or group 2A, but people kind of don't say it. Now, group 3, we actually skip the whole middle section, and we pick group 3 back up right there. So this is group 3. This is group 4. This is group 5. This is group 6. This is group 7. And this is group 8. So that is the group numbering that you should know and that you use in most of your chemistry classes. And once again, it basically is the A numbering, but a lot of people don't kind of include the A when they say it. So groups are 1, 2, 3, 4, 5, 6, 7, 8. Again, groups going down on the periodic table here. Now, when we go left to right on the periodic table, those are what are referred to as periods. So periods go this direction on the periodic table. And we do have about 7 periods on the periodic table. It's not really labeled here, but basically this is period 1. Period 2, period 3, period 4, period 5, period 6, and period 7. Again, periods going left to right there on the periodic table. So groups up and down, 1 through 8 is the numbering we use, skipping the middle part. Periods 1 through 7, left to right on the periodic table. As we talked about earlier as well, obviously, the number above the symbol is the atomic number or the number of protons, right, that an element has. Any questions on that there? Yeah. Say again? It can. For example, the two rows on the bottom are sometimes referred to as the lactinide and actinide series, so it can, but most of the time people call them periods. Yeah. Usually they'll kind of refer to that a lot of times as for those 2 bottom rows as series. But it basically means the period going left to right. Other questions? Now, when we look at the periodic table, it really is broken up into 3 categories. If you look at most periodic tables, you will be able to see right about here. This is like boron, by the way. You usually see this was usually referred to as like a staircase kind of coming down. You can kind of see it on the one on the wall. Usually, for the most part, if it's not drawn there, people will draw it up on it. But that little staircase, to the left of the staircase are metals. Also, the 2 on the bottom, 2 rows on the bottom are also metals. To the upper right of that staircase are nonmetals. And on the staircase are metalloids, or sometimes referred to as semi-metals. And those are the three sort of groups of elements. What is a metal? A metal is a good conductor of heat and electricity. They're also malleable, which means you could hammer them into thin sheets. You could pull them into wires. They typically, metals have shiny appearance. They are also, like I said, good conductors of heat and electricity. For the most part, all metals are solids at room temperature, except for your friend Mercury, which usually is a different color, Hg, on the periodic table there, right next to gold, which is Au, like around number 80 there. And that is a liquid at room temperature. So all other ones are going to be solids except for Mercury. And on a lot of periodic tables, Mercury will be a different color, the Hg, in terms of what's written there. Now, non-metals, on the other hand, have actually just the opposite sort of characteristics. They're usually bad conductors of heat and electricity. They also have a more varied physical state. There are some non-metals that can be gases. There's some non-metals that can be liquid. There's some non-metals that can be solid. They're also dull, brittle, and insulators. Most of the elements that come as diatomic molecules, there's like 7 of them: hydrogen gas, oxygen gas, nitrogen gas, fluorine, chlorine, bromine, and iodide. All of these guys are what are referred to as diatomic molecules. So as we talked about earlier today, molecule is a definition of 2 or more atoms together. Diatomic means you have 2 atoms, right? It's triatomic is 3, so diatomic is 2. And in this case, they're both the same. So like hydrogen, you have 2 hydrogen atoms, which makes them elements. So these sort of, we got there 7, these 7, that is how they normally come when they are by themselves. They do not come as ones. They come as these diatomic molecules: hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodide. And they're also nonmetals, all these guys. And they're also molecules because there's 2 of them. That is usually found up to the right. But as we talked about earlier, when we talk about group 1, group 1 starts with lithium, which is here. That's because this guy right here is hydrogen, right? And hydrogen is what type of element? But is it a metal or a non-metal? It is a non-metal. Everybody else in that group 1 is what type? They're all metals. So even though they're hanging out there, hydrogen on group number 1, it is not part of group number 1 because hydrogen is actually a non-metal. And the rest of everybody there in group 1 is actually a metal. As I mentioned earlier, years ago, sometimes a lot of periodic tables, you would actually see hydrogen written on both sides. So you would sometimes see hydrogen there and there because of the special sort of properties. And the reason for that is hydrogen, even though it's a non-metal, does behave very similar in a lot of aspects to how those guys in group 1 behave in terms of the charges it makes. But because it's also a non-metal, it should technically be over there on the right. But most periodic tables now just keep it on the left. But again, to remember, not part of group 1 for sure. Let's talk about the metalloids. The metalloids are sometimes referred to as semi-metals. They are pretty much where the staircase is, just for overlaying purposes there. Some books, I don't remember if your book does or not, will include boron in it. But it basically kind of comes down this kind of 2-step here. What are those? Well, semi-metals or metalloids are elements that have properties that you could say those are some properties that seem similar to metals, but they also have properties that are similar to non-metals. So the same element will have properties that you could go like that's some metal properties, but also some non-metal properties. Also makes sense based on where it's located, right? Because as you go left to right on the periodic table, you're going from metal to non-metal, and our metalloids are kind of the transition, if you will, between metals and non-metals, and they have properties that kind of fall on both sides of the situation there. Any questions on that there? A couple other important things about the periodic table is certain groups have special names. So group 1, which once again is over here, These are the alkali metals. And once again, that starts with lithium, not hydrogen. Right next door in group number 2, that is the alkaline earth metals. The word alkaline means basic. And that is pretty much in group number 1 and group number 2. If you hook up some hydroxide or OH with those guys, you get things like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. These are all things that are strong bases. So that's where a lot of strong bases come from on the periodic table, group 1 and 2, and that's where those names are derived from. Alkali and alkaline earth metals, again, alkaline merely meaning basic. All the way over there on group number 7 is the halogens. This is your kind of 2-pack of everything, your fluorine, chlorine, bromine, iodine. Those are the diatomic guys that come as 2s. So fluorine, chlorine, Cl2, F2, Br2, I2. For the most part, fluorine, chlorine are gases. Bromine is kind of like a gas with a liquid component, and iodine is more like a solid gas type of deal that kind of happens along the way. Also, the last group, group number 8, is the noble gases. Noble gases means they are chemically inert, they are set apart from others, they frankly are unreactive, is what inert means. They will react with themselves, but nobody else. As we will talk about, group number 8 is really important because when we get into bonding and how things come together to make compounds, the goal is for everybody to end up with the same electron configuration as group number 8. They're super stable, and that ultimately is what everybody's trying to do when you do ionic bonding, covalent bonding, any type of bonding. The goal is to end up like those noble gases because they're very, very stable. So the halogens, as I mentioned before, a lot of them are gases and kind of liquids. They are very reactive, and reactivity actually increases as you go upwards in that group. And they do make acids, like HCl is hydrochloric acid, HF is hydrofluoric acid, HBr is hydrobromic acid. So they make a lot of acids with hydrogen ions, which is H plus, coming together with those halogens to make things like I just mentioned, hydrochloric acid, hydrobromic acid, hydriodic acid, hydrofluoric acid. Noble gases are, if you're finding an old book, they call them rare gases. Nobody calls that these days. But noble gases, once again, group number 8 here at the end. Uh, the 2 rows at the bottom are put in there not to make the periodic table too wide. The only place I've ever seen it actually done correctly is actually our lecture room on those periodic tables that are in the front of the room. And that's because if you look at the actual atomic numbering there, we come here, we go 57, and then we skip to 72. What should go there is actually this period right there. That's 58 and so forth. If we come here, that's 89, and then we skip to 104. This row right here, our period, should actually go here. So those 2 periods technically go right there on the periodic table. On most periodic tables, they don't put it there because, much like the wall there, it will spread your periodic table way long, but they actually go there. That is also why they're called the lanthanide and actinide series, because they follow those elements on the periodic table is where they should go. Where La and AC, lanthanide and actinide, that's technically where these 2 rows should be popped into the periodic table. Now, between group number 2 and group number 3 on the periodic table, group 2 and group 3, all these guys, these are transition metals. One of the important things about transition metals are, as we'll talk about with naming, they can have multiple types of positive charges. They can make, like copper can make +1 in certain situations or +2 in other situations. Now, these guys on the bottom are sometimes called intertransition metals because technically speaking, they should go right there. So sometimes they're referred to the two guys on the bottom as intertransition metals as well. So as I mentioned before, as we go from left to right on the periodic table, we go from a more metal characteristic to a non-metal characteristic. You do need to know where groups are on the periodic table. You need to know the proper numbering of the 1 through 8 groups. You do need to know where periods are on the periodic table, where metals, nonmetals, and metalloids are on the periodic table. You need to know the names of the groups: alkali metals, alkaline earth metals,